Uh, Good morning. Thank you for the introduction, and I thank very much the organizers for inviting me to participate in this conference, especially in this IoT track. I think I need to put this in full screen. How do I do this? IoT missing parts. First of all, I would like to ask you, who are new to IoT in this room? Who are experts in IoT in this room? So maybe having a talk about IoT missing parts for those that are new to IoT may be a little bit misplaced. I'll make an effort to be as clear as possible. If you don't understand anything, feel free to ask. Tomorrow, Gabriel will give you a talk about IoT fundamentals, and you may complement. Today in the afternoon, he'll give a talk about IoT fundamentals, and then you may complement these concepts. When you look at this word missing, something that's missing is something that you don't have. You may not have it because it's really non-existent, or it may be missing because you have too many of them and you don't know what to choose for your application. The common example today is about information. You don't know one thing, then you Google. And then you get so much information that you don't have any information at all. Because either you don't have time to go through all this information, or you don't have a criterion to decide what is the best information for you. At the end, you have a missing information. So when I'm talking here about missing parts, you need to understand this, that something that I'll talk, really, we don't have. We need to develop, we don't have any solution. But most of the things that I'm going to talk today, we do have solutions, but we still don't have the solution, the best solution. For example, I liked very much Professor Sakamura's talk. And in fact, maybe next year, I will increase the number of missing parts because of his talk. I'm not here to criticize his solutions, they are very good. But nevertheless, they are not the solution. They are not the solution for all the problems that you want to solve. And we could go through the architecture that was presented by Professor Sakamura and pinpoint some problems that you may have in different scenarios that have been discussed here. So I will show you some solutions during this talk. How much time do I have? Hopefully I don't need 1 hour. And we can go and have lunch more or less on time. So in fact, I'm going to show you some solutions and pinpoint the problems of these solutions and where we would like to go. Okay? I don't have anything to change the slides. In Brazil today, unfortunately, we have to say, primeiramente, fora Temer. That in English means, first of all, get out Temer. Temer is the new illegitimate president of Brazil that took the power by means of a farce that was the impeachment of our president. This is a political statement. I'm not here to discuss this here, but it's very important that you know the context that things are going on in Brazil. And as I was telling you 2 minutes ago, if you want to get some information about this, don't go to the big media, because all the things that you're going to read are lies. And this will be more clear in the debate, because this is the focus for my talk this afternoon. So, primeiramente, fora Temer. IoT definitions around the world. Michael started the session telling us that he looked for definitions of IoT, got some of them. I like this one for two reasons. The first one is because I worked in this project, the Casa Graça. I read this, a global network infrastructure linking physical and virtual objects through the exploitation of data capture and communication capabilities. This infrastructure includes existing and evolving internet and network developments. It will offer specific object identification, sensor and connection capability as the basis for the development of independent federated services and applications. This will be characterized by a high degree of autonomous data capture, event transfer, network connectivity, and interoperability. I like this definition because I don't understand it even today. It's too complicated, it's too long, but it allows me, then, let me see if I have, yes, to use this definition as I'm a teacher, then to explain it to you and make it more clear. Then you can go back, read it, and you see it makes sense. But it's too long, not didactic at all. Another important statement is that according to the European Commission, for delivering the potential of the Internet of Things, the biggest challenge is to overcome the fragmentation of vertically oriented closed systems, architectures, and application areas. It will be important moving towards open systems and platforms that support multiple applications and to bundle, integrate solution offers. Even without explaining IoT so far, this is a very important statement for nowadays. Even if you are new to IoT, you know about smart cities, smart transportation, smart buildings. These are the vertical silos. This is a domain of application, and you may have optimized solutions for them. But when you have the solution for one problem, this does not mean that you have the solution for another problem in another domain. And the need today is to have horizontal solutions, cross-domain solutions. This is really a big challenge. In this presentation, I will go through these topics: IoT reference model, IoT traffic modeling and estimation, inclusion of pattern recognition and cross-communication in IoT platforms, a horizontal platform focusing equally on the information up and downstream paths, a comprehensive IoT conceptual model, and fast prototyping of IoT solutions. There is another vision, that is the European Union vision. This one I'm not going to read. I think that the presentation will be available afterwards. But as Michael had said, there are many definitions. This one is proposed by ITU. It's not much different from Casagras's definition. But what is more important here is what is written in blue, that over the last 2 years, IoT has moved from being a futuristic vision to an increasing market reality. So a few years ago, when we talked about IoT, this was something that would happen in the future. We are not talking about the future anymore. We are talking about the present. IoT solutions are available nowadays. It's already a reality, even if we don't have the optimal solutions for the end user needs. This is a possible reference model. So this model was proposed in the Casagras project. And I like this model because this is the picture explanation of that very long definition. On the left side of the picture, you have the physical interface zone. This means where the real-world objects are. And by real-world objects, I'm talking about the bottle of water, the glass of water, the table, the chairs, the projector, and even the people. This is the real world. What's important in the physical interface zone is that the objects must be identified. You must have some means of identification. You may have an identification that's just a barcode that you know quite well. Look to the bottle of water that you have in front of you. They have a barcode. It could be an RFID tag. It could be any means of identification. Important point is that this identification can be read electronically, automatically. And when you read this identification, it goes through the interrogator or gateway device, and then you have a representation of this object in a computer. You have a virtual representation of this object. And you see that this path going through the physical interface zone to the virtual representation on this host information and management systems is the same thing that Professor Sakamura has presented, maybe with a different name. So the object of the physical world now has a virtual representation. If it has a virtual representation, you can navigate through it. As you navigate you can browse this object, as you do in the internet. What is the convention internet? You have information that is stored in computers around the world. And then you have an address, an URL, and you can find this page and you get the information. Now, this object also has a locator, and you can browse this object. So with the information that you get from the object, associating information that you can get through the internet, you may describe a context, a situation, and make a decision about an information to display or an action that you take upon either the object or in the environment. Simple example, you may have a sensor in this room. This is the real object. It can be read. the information about the location of this room and its temperature goes to the host information management systems. Then you have an application that is running on top of that, and they see, well, this room is at 29 degrees Celsius. We have a conference, and we have a talk at this time. 29 degrees, it's too high. Let's decrease the temperature of the room, acting upon the air condition. And then you have the complete cycle that ends with the actuators. So this is the complete cycle of the Internet of Things. It starts in the physical zone and it goes back to the physical zone. You can have variations as the actuation, let's say, it's limited to displaying an information on the screen, and then the human, the person that's reading that, may decide by him or herself what to do. So this is the main idea of the IoT definition. And this is a reference model. Reference model is a kind of template that helps you to understand what the system is, and from then you can develop your architecture, and from the architecture you can develop your application, your solution. IoT traffic modeling and estimation. So now I really start talking about the missing parts. We need, if we go back to the model, we have information that's going through the internet. So this information means that we have a new traffic that's going through the internet. What is the characteristic of this traffic? It's high speed, it's low speed. Is it sensitive to delay? Is it sensitive to packet loss? What are these characteristics? How will this traffic increase? So we need to know what is this traffic, because we need to assign resources to the network in order to guarantee the quality of service from end to end. And in fact, we don't know this traffic. It's a new traffic. We don't know its characteristics. And its characteristics may depend on the kind of application. We don't know how is the interaction or the influence, for example, from this traffic that comes from the sensors with the traffic that comes from the cloud. Because, for example, you may have a job that's being processed in a cloud node. But then for even business reasons, you want to move this processing from one cloud node to another cloud node on the other part of the planet. Then you have a huge traffic that will be traversing the internet at the same time that you're getting real-time data from your sensors. What will happen? We simply don't have this answer yet. This is a missing part, the traffic aspect of IoT. In this slide, that's part of a proposal of a possible project. We can even try to understand this traffic, taking into account different applications. Because of this, we have the public transportation stakeholders and the public health stakeholders. To do this, so you have the two stakeholders or the applications that you are trying to understand. Through the internet, you have the traffic that is flowing, and then you need to install traffic monitoring units to capture this traffic. So you capture the traffic and you proceed to a traffic analysis. that's made of traffic classification, traffic modeling, traffic forecast, traffic matrix estimation, and even traffic generation if you want to simulate this traffic in the lab to understand better the behavior of your applications. So all these topics, traffic classification, traffic modeling, forecast, metrics estimation, and generation, are research challenges that must be solved. There are much theory, much things that were developed for this, but they were not developed for IoT. And you see on the left side, we have governance guidelines. Why do you need governance guidelines here? For example, privacy. I'm talking about real traffic. Real traffic may be the room temperature in your house. It may be the energy consumption in everybody's house. Can I access that? Do I have the right to use this information, even if I'm not interested in the content, the information itself, but just the traffic? I need to have rules to do this. I need to anonymize the data. So this is not only a technological problem, but we need governance guidelines to understand what's going on here. This is still about the same topic. I know that this is small, but from the information that we can get from this experiment, we may arrive at two types of conclusions. Let's say one set of conclusions would be, what are the limitations of the internet, the current internet, to take care of this traffic? And when we understand what these limitations are, then we may have two kinds of solutions: the short-term solutions and the long-term solutions. The short-term solutions means that I may improve a well-known protocol. I may add some functionalities, and then I may solve part of the problems. I may even know that I will solve the problems for a period of time, but it will not last with the increase of traffic. And I may also have information, enough information to path towards the future internet. Will the internet, is it possible to continue to have the internet with the architecture that we have today? I don't know the answer. Even if I don't know the answer, I know that there is a conflict between it's reasonable just to think about the evolution of the current internet, but this evolution may not be good enough to deal with all the problems. And we may have to start from the scratch, meaning that to have a different architecture for the internet, for this network to be able to cope with the problems that will arise. So this is a missing part in the sense that I don't see a structured project that is looking at these aspects to thinking about the future internet, considering the traffic aspects that come from the Internet of Things. The IoT platforms. There are many platforms in the marketplace. I chose to talk about this one, the Link Smart architecture, because in my lab we use this platform. Now, this platform is the result of an European Commission funded project in the program FP6 program, and it was developed by the Fraunhofer. The project was called Hydra. By the end of the project, they renamed the platform due to a commercial conflict with a product to Link Smart. This platform is written in Java. It is open code, open source. It is for free, so you can use it the way you want. It's a very complete platform. So when you look at this platform, first of all, you see that on the left side, you have the application elements. On the right side, you have the device elements. This meaning that you have part of the platform that is running on nodes that have processing power. These are the application elements. And part of the platform was made to run on the devices. The devices are very tiny. They don't have much processing power, energy, storage capacity, and so on. So it's a simplified version of the left side. You have several layers, meaning that you have different services that are necessary to implement an IoT application. So this middle part is the set of IoT services that are necessary to implement an IoT application. The applications are on the top, and they access the IoT services by means of APIs with open interface. And on the bottom part, you see that it's operating system agnostic. It can work with different operating systems, and also at the physical layer level, different technologies can be used. So this is a very general platform. This is a very powerful platform. It works. It works well. But when we decided to use this platform, we noticed that something was missing in this platform. And as it is an open platform, what we did? We introduced a new layer that is a pattern recognition layer. The main idea of this pattern recognition layer is to change the level where you do some data processing. Because you receive too much data from the physical world, but not all this data represent useful information. So it makes sense to process part of this information, to filter this data, and deliver filtered data to the applications. This goes in the direction of dealing with the scalability problem in your architecture and not sending everything to the application level. So that was the idea, to introduce the pattern layer. In this pattern layer, it uses big data technology, and you can introduce any kind of algorithm that you want. We implemented a few algorithms just as a proof of the concept of the architecture. And this is an example of a clustering algorithm. So we have the original data that were received from the sensors, and the idea was to classify this data into clusters. So we implement a clustering algorithm that in this case identified five clusters. The innovation is not the algorithm itself, it's a classical one, use the k-means algorithm, but the innovation is that it is implemented in the platform. The other aspect is the cross-communication Here is a detailed view of what we've done. You have the pattern manager. The pattern manager that is implemented in a powerful node. But you can also have in the bottom layer what's called the resource layer, the resource manager. You can implement these algorithms close to the device. And you may say, this makes no sense if the device is too tiny. This is a wrong idea that we have about IoT. Today, when we talk about IoT, we always say the sensor is too tiny, it is mobile, it depends on Wi-Fi, so we need to put everything into the application level. This is not true for all scenarios. For example, if you take a petroleum refinery and you're going to do the control of the process, everything is fixed. Nothing is mobile. The sensors must be put in specific places because they must be put close to where the process is done. You have no restrictions to have a very tiny sensor. You may have a powerful one, and it may get too many data to be transferred to a central node to be processed. So it makes sense in some scenarios to have the processing close to the resource. And then you need to switch to tell not to tell the application needs to tell the platform where to process the data. And because of this, you need the cross-communication between the IoT services layer and this resource layer. And this cross-communication is not common in the architectures that you see. So this is another point that we identified that could be introduced into the Link Smart platform. So you see, it's not a critic to the Link Smart to say it's not complete. It's right on the contrary, it's a very good platform that allowed us to enhance the functionalities because it's open. And now we have a better platform. If it were a closed platform, we simply could not solve the problem. And this is not for sure the final answer. You may identify other problems that demand a solution that's not contemplated here. Now, another topic. A horizontal platform focusing equally on the information up and downstream paths. The problem of the vertical silos. This is a classical figure about providing IoT solutions for different applications. So these names in the middle as Carrots, Shively, and so on, these are commercial IoT platforms that you may buy and develop your solution. And here we have different domains. Even myself, I can't read this, but you have transport, education, health, entertainment. Each of them is a domain. So now I can read transport, education, health, tourism, food tracking, entertainment, finance. And you have an optimized solution for each of them using a specific platform. So this is the common scenario nowadays. And this scenario, even though you have very optimized solutions for each of these domains, it does not solve the future problems. Where, for example, we may have an interest to develop a cross-domain application, including health, tourism, food tracking. This is a very simple example. You have the farms where you are producing the vegetables and so on. They need to be transported according to some conditions. And then we are going to the supermarket to buy this. You may want to know where it was produced, what was the conditions of transport, what are the health characteristics of the food that you are buying. So you need information from different parts. And you are sitting here. This diagram is reversed. The application is in the bottom. So you want to be here with your application, your cross-domain application, and you need to get the information from the different domains, eventually accessing these different domains by means of different platforms. And this is not trivial how to do. Even you may not have a good solution to solve this problem. So another proposal was to introduce in this architecture an intermediate layer made of two sublayers. The first one is the physical resources and network abstraction and virtualization layer. And the second one is the physical resources and network instantiation and configuration layer that will allow, when you are sitting, in this case on the top of the application, to be able to access any domain going through any specific platform. And here I have also introduced one that is very important today, to have a horizontal platform based on the 1M2M international standard. Another detail of this diagram is that on the left side you have the IoT upstream processing. This is the sensing path. You get the data from your sensor, you send it to the application. Hopefully, from the data, you get the information, and you're able to do what you want. And there is much information, much research about this upstream path. Everything that you read about semantic annotation deals with this upstream path. Because you have the data, you need to annotate it semantically to the data to get meaning to be processed. But you have the other path, the actuation path. You have the make decision process that is running on top on the application, and then you decide that you need to turn on the air conditioning. And not much is talked about the actuation. But the actuation path is really very important, because you have applications, for example, an industrial plant, that are quite sensitive to the delay. If they are quite sensitive to the delay, this architecture makes no sense, in the sense you don't have time enough to send the data up to the application and then it to come back to the actuation. It's too long time. So you may also need to have some reasoning process at the bottom level to decide about the actuation. So we need to look at this downstream path and find better solutions for the IoT applications. Another missing part. This is an IoT conceptual map. Conceptual maps we use to describe a concept, an application, a problem. There is no right conceptual map or wrong conceptual map. It depends on the view that you have of a specific problem. I consider the conceptual maps quite useful. For example, when I have a new PhD student or a master's student and we discuss what is going to be done, then I ask the student to develop the conceptual map. The conceptual map will tell us briefly the story of that research. This is a possible IoT conceptual map. You have a problem, you define a use case. From the use case, you generate specifications. These specifications are translated into services. And this service require validation. This is where the testers come to the fore to make their work and to prove the technical correctness of what was developed. And from this test, this validation process, you may generate corrections, new specifications, and then you have a cycle that is going through as many times as necessary to arrive at the right service. This is very common. There is no novelty here, and you may recognize that in general, this conceptual map is what's used for developing engineering applications. And I say that is incomplete. This is another incomplete IoT conceptual map, but I ask you to keep this information inside this room, because this was the conceptual map developed by a PhD student of mine. He would be very sad to know that in Malaysia I said that his conceptual map is incomplete. He's got his PhD, so there is no problem at all. And I put it here just to show that the conceptual map may be very, very complicated. It can go deep into the details. This is the conceptual map that led to the development of the pattern recognition layer of the platform. This was the start of the story. So this is a very detailed one. In fact, it's a very good conceptual map that allowed us to identify the needs of development of that pattern recognition layer. But I insist that despite of this being very crowded, it is an incomplete conceptual map. And why? I will arrive at the complete conceptual map. But we need an intermediate step. That for me, it's really very important, and it is very important now for some years. This is the harmonized integrated architecture framework leading towards realistic roadmaps. What you have here on the top plane, the top plane is the technological plane of IoT. When you traverse this technological plane, you see the different needs, technological needs to achieve a given application. What you need in terms of the backbone, what you need in terms of the interface, and so on. It's represented on the top plane. But this is not IoT. IoT, in fact, is driven or influenced by the other planes. If you don't take into account security, business process, integrated management and control, regulations, governance, standards, and human factors, you don't have IoT. Or at least you don't have useful IoT applications. This view is simple, but this is not just to have a beautiful slide. How do you use this in practice? How, let's say, a problem in regulations may influence the development of an application? What is the interplay between these planes? So when we have a problem to solve, an IoT application to develop, we should start by a feasibility study. A feasibility study should identify what are the obstacles that you need to overcome to get to the result. And many times we look only at the technological level. We don't have this technology, we need to develop this technology, we need to buy this technology. But we're not looking, what are the regulations in the country? How are we going to protect the end user of this new application of service? What is necessary? What will be the interface? What are the influence of the new application on the end user, on the people? And many times, according to some studies that we've developed, the main obstacles are not technological. They are on the other dimensions of the IoT. So, for me, or the people that I work with, we consider this diagram very, very important and should be the basis of IoT development. And taking this into account, we have a comprehensive IoT conceptual model. The difference of this model, it does not start with the use case. It starts up there, society. And starting from the society, we need to identify the needs. From the needs, we need to identify the contexts. From the context, we have two possible alternatives. We can go directly to specifications, generate specifications, or it may be too complex to go directly to the specifications. We may suggest use cases, and from the use cases, generate the specifications. The specifications translate into services that require validation, that measure the technical correctness. This is the same as before. But then we add that the validation should measure the need satisfaction. That should also correct the specifications. We need to compare what we've done against the needs, not only against the specifications. When this cycle is complete, the services will produce some social impact. It may be positive, it may be negative, but it will produce social impact. And it requires assessment and evaluation that may also correct the specifications. And this social impact transforms the society and the cycle runs again. Because after you run the society, you run the cycle and you have a social impact, the needs change. Yes? Yes, you could do that. It's an interesting change. Could do that. Don't have anything against. You mean coming from the... Yes, instead going through the specifications, going to the use case. Yes, I agree. You can do that. But a simple example to show you that this cycle may run many, many times. We had a meeting yesterday that I mentioned that next week a student of mine will present her master thesis. And she developed a study of an education application that integrates the educational entities with the health system, with the transport system. So the idea of the cross-domain application. But let's just focus on the education. If you developed a successful education program, you have better qualified people at the end of the process and after a few years. And better qualified people have different needs from other people. So, after the social impact, you have a different society. If you have better qualified people, you need better paid jobs. So I wouldn't say this is an infinite cycle, but it's important to see that this cycle means that we can change the society, hopefully in a positive way, and change the society, we have different needs. Another very important observation is about needs. The sociologists say you cannot talk about needs. This makes no sense. Needs is attached to a context. If you talk, what is the transportation needs of the people? This question makes no sense. If you don't take into account income, age, where they live, they want transport to do what? Needs, transportation needs makes no sense. It's completely empty. So we need to define contexts. Only defining precise contexts, we can really identify needs and produce services and applications that are useful to the society. Otherwise, you may have case studies, use cases that are very good to write papers and to have conferences and then to discuss among the professors the best paper presented in this conference. No one will use that. This doesn't matter. But if you want to change, to be useful with our work, we need the comprehensive IoT conceptual model. Fast prototyping IoT solutions. This is another idea that maybe we can discuss further about collaboration. And this is very pragmatic. How to produce IoT solutions very fast? How can we test our ideas very fast? And this is not despising the former concepts, but just to prove new ideas, test them, and learn from experience. Instead of having a 3-year cycle to produce a very good application, let's produce something in 3 months and learn from this experience. The idea is to bring to this IoT environment the Scrum concept that people from software know very well. I'm not from software, so I don't know it very well. Scrum is an iterative and incremental agile software development methodology for managing product development. It defines a flexible, holistic product development strategy where a development team works as a unit to reach a common goal. So the idea is to have different cycles. We start with a set of specifications, develop them very quickly. And with this development, let's say the objective is not to have the IoT solution, but to test your environment. What you need as tools, what you need as framework, what you need to improve your specifications, and learning from this experience, you go to the second one, and then you can test or can prototype very fast IoT solutions. And this may be interesting to think about developing a project to do this. I'm arriving at the end of my talk. In Brazil, we created the iRiot. iRiot is the interdisciplinary research for the Internet of Things, and it has been created by a group of professors from the Escola Politécnica, the engineering school where I work, the law school, the School of Communication Arts of the University of São Paulo, to develop joint research. It is the materialization of the common knowledge that IoT is interdisciplinary and multidimensional. Its first initiative is the development of the building blocks of research for the Internet Connected Objects, the BRICS project, that aims at creating a tool to build realistic IoT roadmaps for Brazil and South America. The BRICS is the diagram with the different planes. It is open to everyone who has questions about IoT. Answers are not welcome. And as was said, I think about Blaise Pascal, la réponse est le malheur de la question. The answer is the bad luck of the question. So we have this cooperation, iRiot, the Knowledge Seat, the University of São Paulo, Perception, Brazilian company, Gabriel is the president, the Brazilian IoT Forum, and now the UPC, the Technical University of Catalonia, where I am invited professor, University of Geneva, University of Bournemouth. Results in a group of professors, PhD researchers, developers, social scientists, entrepreneurs, businessmen that collectively have the human capital to face IoT development challenges. To end, this is the very end. As I said, I'm a visiting professor at UPC that has a PhD program. It's open to everyone, so we invite, if you are interested in studying in Spain, get your PhD. There is a very good PhD program in computer architecture. You may have all the information here, people to contact, and even you can get scholarships to fund your stay in Spain. Yes, you can apply for grants either from the Spanish government or from the government of Catalonia. There are grants from two sources. So this is really an invitation. We are interested in getting PhD students. So thank you for your attention.